Let's recap. So last time we talked about time a bit, and we talked about how time is a measure of rate of change, how things change in location with respect to some standard that's always oscillating in some predictable fashion, and how all of our clocks have little flaws and we have to triangulate them. And we talked a bit about climate, which was very nebulous, and we tried to make sense of how the climate changes, and obviously people are still trying to make sense of it to this day. And then we talked about seasons, and so I was hoping to get into calendars a bit, and I want to get on to the moon as soon as possible, but really quickly I want to just go through and talk about how we got our modern calendar, because there's a few little interesting changes that have occurred over the past couple thousand years. Obviously, folks have had more or less a calendar with a 365. This has been one of the first, rudimentary clocks that we have, is that the sun appears in the same place every year. And so I want to just get through the calendars quickly, and then I want to get into the moon, because there's so much to say about the moon, and for better or for worse, this is the only point we really get to talk about the moon. We're going to go through each one of the planetary bodies later. We're going to talk about the different classes of planets, and we're going to really get into the nitty-gritties of it, and we'll talk about other planets' moons, but our moon we only have today, and we need to talk about all the effects the moon has on our planet here, which turns out to be quite a bit. It'd be a very different place without a moon. And I also want to talk about the moon itself, because the story of our moon is, just like everything else in astronomy, is being updated continually. I don't know if you guys realize it yet, but astronomy is one of those places in science that is just so on the cutting edge. We're changing our mind about everything by the day. If you pay attention to the headlines, things are being updated, and even how we think that the moon came into being has changed in the last 10 years. So, I was trying to find some videos of the moon's formation, and we'll get to that. And I found one from just exactly 10 years ago that was completely different from the one that's being put out by NASA today. And so that's really wild. You don't get a chance to see a lot of that in other sciences, right? More or less understood that DNA encodes proteins for, almost 100 years now. Well, 75 or so. So astronomy is changing constantly. And then we're going to talk about eclipses, which are pretty cool. And eclipses have had just a wild history in terms of people interpreting what's going on. Because
I was going to ask, what was the video saying 10 years ago about the moon?
Oh, we'll get there. Yeah, don't worry. Yeah, it's interesting. It's actually a very incomplete story, too. That's what's really cool. Is I really want you guys to come away from this class with the opposite of the feeling I had when I was in college, which was that everything was pretty much sewn up in science, and the stuff is all written in the textbook. We basically are just filling in details. It couldn't be further from the truth, especially in astronomy. There's just so much that isn't understood. That's not to say that we're morons about things. It's just that there's a lot of blanks and a lot of things that are halfway understood. And the timelines of that are just shifting so fast. It's quite remarkable. So let's talk very briefly about the modern calendar that we use. I would love to have had time to talk about other calendars, but our calendar is essentially based on the solar year. By the way, the solar year, which is 365.2422 days long, is technically called the tropical year. And I'm not quite sure why that is, actually. But the month is 29.5306 days long. And of course, the Earth's rotation is 1 day. And so getting all of those to coincide has been an impossible task over the years. And every single culture has smashed their head against the chalkboard trying to make that work out. And it hasn't worked out. And so really the first people to give up on it were the Romans. And so before we get to the Romans, we should think about the fact that plenty of other cultures had calendars, and they set up giant wheel systems to be able to track or really to be able to plan ahead for the coming solstices. And so one of the most famous ones, of course, is Stonehenge, and it's a really magical place. I hope you each get to visit at some point. And there's a lot of other really incredible archaeology out there in the countryside of England, of which so little is known. You know, we've mentioned before, the Romans did an incredible job of destroying all of the culture wherever they went. Even to this day, if you consider us descendants of the Romans, our culture anyways. And so most of these people's history was oral. They sung their history. So they had a priest class, and the priest class would keep all of the records in history and law, and they would create these really songs, right? These poetic verses, and those would be taught to the next generation and the next generation, the next generation. So they had no, that we know of, they had no written record of these things. And so it was a disaster, because if you kill off the priest class, that's it. You lose everything. And it's kind of tragic. So Stonehenge was, this is actually fairly recently that people have been starting to think of it as a calendar. Stonehenge looked a little bit different a while ago. This is what people think anyways, that it was actually a platform upon which the announcer could stand and divine these various astronomical events. And what folks have determined lately is that they actually use this as a monthly calendar. So each day of the month, they would put a stick in the ground or some sort of way of marking which day it was so people could keep track. And these weeks were like, this is vaguely divided into weeks. It's not clear that they had a week in the same sense that we did. And other cultures also didn't necessarily, you know, this 7-day week thing was a bit later. This is more of a Greek-Roman tradition based on the names of the planets and the sun. We talked about that in the first lecture. So folks have been doing this for a long time. We're going to talk about the Mayans, hopefully, if we get to the end. And the Mayans also seem to be very, very meticulous about keeping track of time. What's really interesting about the Mesoamerican people is they didn't seem so much obsessed with the solar calendar with respect to the lunar calendar. They had this really particular obsession with Venus, actually. This is El Caracol. This is in Chichen Itza, which is a site, a very easily accessible site on the Yucatan Peninsula. I also hope you each get to visit that. I had the fortune of going when I was a little kid before. They've actually closed a lot of the sites, so you can't really walk up on the temples and so forth. But these portals at the top of this cupola aligned with various phases, various moments of Venus's transit. And Venus seems to have been a really important, represented a very important deity to them. And we'll talk a bit about how that came into play with eclipses later. But the Mayan calendar was called a calendar round. And yeah, let's see. This is what it looked like. It was essentially a series of wheels where you had days and numbers, and you could come up with something that approximated a week this way, but the days and numbers didn't repeat themselves. Let's see if we can play that again. That didn't totally repeat themselves for a very long period, something like 52 years, right? And then you would start all over again. And what's very interesting about, and there's even a longer wheel that this whole sprocket system fits into, which is called the long count. And the positioning of these dates seems to actually have had something more to do with the mythological traditions rather than with the astronomical observations, which is quite unique. And what's really weird is that the long count appears to have started somewhere in early August. Let's see. In 3114 BCE was the start of this very long, they would call this the long count calendar. And the long count calendar went for 5,128 years. So that was when you may have, I don't know if you guys are too young for this, but there was a big kerfuffle in 2012 because that was the end of the long count cycle. So people have tried really hard to fit it to different things, like so that's the thing, right? That's the problem. That's the thing with astronomy and astrology in general is if you look for patterns, you can find them. And so people to this day spend a great deal of effort arguing about the start date. And it's very strange because it didn't start on like a solstice or something that would make a lot of sense with respect to our understanding of the calendar. But people have tried to peg it to Venus. You know, there's always the very real possibility that we completely misunderstand something in terms of how we're translating these dates. There's also the very real possibility that there was just a small inaccuracy that built up over time, so maybe it actually did start on some sort of equinox or a solstice. It's not totally clear, right? So the Mayan code it was broken, I think, in my lifetime, if not in the 70s, maybe a little bit before me, by essentially a single archaeologist from the States who went down there and made sense of it, named Michael Coe. And so we know so very little. We're still piecing together all of this. And it's a really interesting mystery. I read a little theory that the original long count date, so one whole 5,000 odd year cycle before the 3000 BC date, that they were able to detect some atmospheric anomalies in that period, and then again at the 3000 BC mark. So some geophysicists have argued that there was some sort of cosmic event, you know, whether it was, I actually don't even know what they have in mind. They call it just like a cosmic event which could have altered the atmosphere. And as we saw last time, there's so many factors that go into affecting the climate. It's very difficult to say what it would have been and what it wouldn't have been. You know, supernovas, which we haven't talked about much, I think we'll do more of that next semester. But supernovas are, of course, one way that stars are proposed to die. And there's certainly something that we can see periodically, but they don't last very long in the sky, right? They literally can last maybe just a few weeks. At most, we see things that look like maybe remnants of supernovas, but it's very difficult to say. But if there were a supernova, that could, of course, dust us with all sorts of a proximal supernova. It's difficult to say, right? Because there wouldn't necessarily be anything left but some traces of that. And so there's some proposal that there was a cosmic event, and that was when they considered, they started keeping track of time, and then when that same cosmic event, let's say it was the supernova or anything else, maybe a comet that we're not aware of, something like that, that they restarted it, and that's how they set the length of their long count. Of course, in the West, it's a little bit different. So, like I said, the Romans were the first people to really come along and decide, okay, hey, the year appears to be 365 and a quarter-ish days long. That'll work. And so Julius Caesar instituted this calendar, which is more or less the precursor to what we have today. And it worked really well for a while. And even built in this concept of leap years, right, to account for that quarter day. So every fourth year, you add an extra day, no problem. And the issue was that it's not quite 365 and a quarter days, right? There's this little fraction of it. It's actually something like 11 minutes more every day, every year. And this wasn't a problem for like a few hundred years, but it became a problem. And so it got to the point, actually, by 1582, the first day of spring was happening on March 11th instead of March 21st, when the equinox is supposed to be occurring. And this is a problem because if you keep going like this, you're going to end up with having your winter celebration, in the fall, and things are just going to be completely messed up. So what they did was kind of funny. Pope Gregory VIII, who was around in the time of Galileo, he decided just to ditch 10 days out of the calendar. So that brought the vernal equinox back to the 21st. And all of a sudden, October 4th turned into October 15th one day. Okay? And then to account for this fractionation of time that was missing with the leap years, he decided that, every century year that were divisible by 4, just like so for our leap years, but they weren't divisible by 400, that those would not be counted as leap years. This is a very complex system. But it works. And we use this today. And it took a while for people to adopt this. Actually, the colonies in the States didn't adopt it until the 1700s. The Russians didn't adopt it until the Bolshevik Revolution in the early 20th century. So this is somewhat new and updated, but it seems to work to this point. But ultimately, it all comes down to the motion of the Earth around the sun. So could the calendar be improved? Probably, and perhaps we'll see that happen. But if anybody doesn't have questions about calendars, I want to dive into the moon. Yes? Ooh, that's a great question. I'll have to get back to you on that. I don't know. Very good question. Yeah, I'll write that down. I want to get into the moon next. So the moon was essentially a mythological creature for most of human history. And then, at least our lingual tradition goes back to the Greeks, so it's easier for us to understand what their thoughts were about it. And the Greek tradition of really scientifically, that is, giving like a material explanation for the moon, started with Anaxagoras, who, if you'll recall, is kind of the hero of Western astronomy because he had the idea of the sun being at the center of the universe, which is, close enough, long before Copernicus. And it seems like Copernicus actually got his idea. I mean, that might be going too far. There's a very good possibility that Copernicus had read Anaxagoras and realized this. But Anaxagoras, he understood that the Earth and the moon were spherical rocks. And this was quite revolutionary. It was so revolutionary, nobody believed it. And he was also kind of amazing, too, because he understood that they were hot, right? That the sun was a hot rock, and that's why it was glowing, which is very close to how we think about it today, maybe even closer to how we think about it later. And so, another thing that Anaxagoras came up with was the concept of panspermia. So this guy was just quite a thinker. So does anybody know what panspermia is, this idea? This is the idea that life can travel between different worlds. And so many of you actually mentioned in the first response video that you wanted to get into talking about the origins of life, and we're going to do that. There is actually time for that in a later lecture. But one of the arguments for the origins of life is that it came from somewhere else. And so I think that this guy is just so far ahead of his time. It's wild. It's wild to think that someone could be thinking that far outside of the box. And what's really interesting about people who think outside of the box is they're always treated as crazy, right? You're always just a lunatic until you come up with something. Yeah, and I was gonna say that people actually thought that Mars might support life until very, very recently, because when you look at Mars with a telescope, you can see that it periodically darkens with the seasons, and people thought that this was something like marshes happening. The abandonment of the hope that life would be somewhere in the solar system has come very begrudgingly, and even to this day, there's many that are hopeful we'll find life beneath the ice shelves of some of these moons in the distant gas giants. And so people have surrendered that very begrudgingly. I was watching, do you guys know who Carl Sagan is? Are you too old for your time? A little bit? So I went back and watched some of the Carl Sagan videos, and this is recorded in the 80s, and he's very hot on the idea that Jupiter might have life, like these breathing, floating parachute creatures in the atmosphere. That's right. Yeah. Yeah. So, and there might be. It's not entirely unreasonable, especially with a panspermic mechanism. You know, actually, the origins of life, there's just so much to say about that. I think we should probably save it. You know, the people who are at the cutting edge of this, there's a gentleman named Nick Lane who's in the UK, and we're actually going to have him on the podcast this month, but he's trying to work out the chemistry of how you could actually make life de novo, right? So we don't see life just happening on the Earth, right? It's not like we ever look out and see just a new species that's not coming from another species. So it's almost like there's a physical law that life must come from other life. Except that makes a problem because then it's like, well, where did the first life on our planet come from? And if it came from another place, well, where did that come from? And so can you kick it down the line? At some point, you run into the concept of the birth of the universe, which is another problematic concept in science, right? Which is in some sense inherited from a religious tradition, which is quite fascinating. Fun fact, the Big Bang was actually invented by a priest who was also a mathematician. So anyways, we'll get into that later. So Anaxagoras, right? So he nailed it, and everybody promptly forgot pretty much everything. This guy, he said, "You're crazy. What are you talking about?" And the Chinese Han Dynasty also had this idea that this was in like 200 BC, so a couple thousand years ago. They had some idea that the moon was just reflecting the sun's light, which was actually quite revolutionary in that day. And the Indians caught up to that by about 500 AD, also with the same idea. And then the Islamic astronomers did a great deal of work observing, right? They were very meticulous note keepers. And actually the Islamic people, by this way, to this day, I don't know if any of you are Muslim, but there's a lunar calendar that's still sort of the rock bed of the Islamic world. Obviously, those people in their Western enterprisings deal with our calendar, but it's still very important for the ceremonies and so forth. So not everyone gave up on the moon as a source of keeping track. So Galileo made this is Galileo's drawings, actually, and we talked about Galileo because he had the first really decent telescope. And he was kind of the first person to realize that there was features on the moon. It was very rocky looking, and there was these cratered pockmarks, and his drawings weren't bad at all, actually. And then, you know, by the way, this is in like early 1600s. Within a few decades, everybody was doing it. This is some of Robert Hooke's drawings. Robert Hooke is also just one of those complete superheroes of science. And I forgot to mention this, but there's some thought that Robert Hooke gave Newton his inverse square law, and they were squabbling over the credit for this to the very bitter end. But Robert Hooke's most known for his concept of elasticity, the spring constant, which is really important to me from a material science background. So this is what I did my PhD in, was in these elastic harmonics. And Robert Hooke came up with that basic idea that substances have each substance has a unique deformability to it, and that the ability to stretch it can be described by some constant, which we call the spring constant. You'll probably do that in your basic physics classes. So people were, in this point, this was about 500 years ago, people were really starting to get hot on the idea that the moon was some sort of a planetoid type thing, and that there might be interesting stuff going on over there. And it continued, people continued to embellish on this. Folks all the way up into the mid-1800s were hell-bent on the idea that there was life on the moon, actually, and they would see it, right? They would see what they wanted to see, which is a really fascinating cognitive bias that humans have. You know, have you guys heard that term cognitive bias? Like where you're used to seeing something, you're used to it happening, and so you kind of make it happen. There's actually something like 200 established cognitive biases, and so what's really fascinating is the cognitive scientists are now looping back around, and they're like, you know what? I think that there's so many cognitive biases that we don't even understand cognition. Like the way that we thought humans worked, if there's 200 things broken about it in every person, we probably don't understand how people think very well. And so there's quite a revolution in cognitive science right now, which is quite fascinating. If any of you are interested, that's a very ripe field for development. So eventually we started putting satellites in space. The Soviets actually made it out there first. This is the first picture they took from near the surface of the moon. The name of this space probe was Luna 6, I believe, Luna 9. So they sent several probes on flyby missions and got closer and closer. And I would love to do, if you guys want to beg your administrators for a course on space exploration, that would be a really cool class. There's so much to say about the entire enterprise of getting out there and space mining and what's going to happen. And I think it's absolutely relevant. So that'd be a really cool upper level seminar if somebody wants to beg somebody important for it. But we don't have time to really do the space exploration. So needless to say, there's been all sorts of journeys out to scope and scoop up pieces of the moon and bring them back. And it's going to be a wild next century because there's certainly plans to get out there. There's the Artemis mission right now. What's up? Yeah.
Wasn't there a Soviet probe that tried to go to Mars, but it didn't get in orbit?
I'm sure there was many.
I remember there was something about it. If probes do crash, and wouldn't the data still be on them?
I'm not sure, and I'm not sure about like the Mars missions, right? Off the top of my head. I mean, I think there's just I think it's an amazing story. That's why I'm like, we need to have a class about space exploration. Like, it's too rich. What's up? What is the moon made out of? Yeah, we're going to talk about that. So it's called regolith, which is just a fancy word for rock. The moon is actually very similar in some respect to the composition of the Earth, and this is what's really giving us some pause for panic about the formation of it, because we're going to talk in just a second about the different ideas people have had about where the moon came from. And none of them are particularly complete right now, and that's super exciting. The fact that, there was this huge space race, right, to get to the moon. Just a quick aside. The fact that the Americans said, okay, we got to the moon, and the Russians basically gave up is really something that stumps me, The Russians really, they must have believed it really, really hard for some reason. And I can't quite figure that out if they had their own spy satellites watching the whole thing or what was going on. But, the Russians pretty much just gave up on the space race at that point, which is really fascinating to think about. All right, so planets and moons. What is a planet? This is probably a good time to talk about that. It's a very fine line, and actually, where do you draw the line between a planet and a star is another fine line that we're going to keep crashing back into. Because there's these big Jupiter-like planets there's stars that are smaller than big Jupiter-like planets, right? And so the idea is that if Jupiter-like planets get big enough, they collapse and crush themselves and fusion is ignited. This is the standard model of star formation, which is on the ropes a little bit. This is tricky because you have overlaps where it's not quite clear what's going on and what causes something to start glowing versus not. And of course, actually, Jupiter is giving off a fair amount of light if we mean that by the total radiation given off by it. A lot of it is in the radio wave frequency spectrum. But so what is a planet? It's an ever-evolving definition, and this is fascinating, but we have to draw the line somewhere. So the planet has to have cleared its neighborhood of all the dirt and dust and debris. So there's a couple of roundish bodies out there in the asteroid belt. Anybody watch The Expanse? That was a good one, right? So there's a couple of these roundish ones, Ceres and Pala. And they don't count as planets because they haven't cleared their field. So that takes them off the list. You also have to have sufficient mass for your self-gravity to overcome to squeeze it from all directions such that it turns into a sphere. This is called establishing hydrostatic equilibrium, which is kind of shown here. It's this balance between outward and inward forces. This gets really strange because, again, it doesn't seem like all of the spherical bodies have sufficient mass to established hydrostatic equilibrium. So people are kind of scratching their heads, particularly with respect to, I believe there's a moon of Saturn. We'll talk about that more later. That's not quite big enough. It doesn't make sense. I mean, obviously, the solution is that it used to be bigger, right? And we can talk about that more later. But the main defining feature that removes our moon from the planet pool is that the planet has to be in orbit around a sun, right? Obviously, the moon is in orbit around us. So here's a couple of those bodies there's Ceres and a couple of oblong guys that aren't quite, that are claimed to not be big enough to crush themselves into a sphere. It's one of those paradigms that I think is going to shift in your lifetime, because we have to start thinking in terms of how long these bodies may have been out there. We talked about the Oort cloud before, which is at the edge of our solar system, and how there's perhaps other planets drifting around out there. And perhaps even one of these planets can be periodically destabilized by the passage of other solar systems by us. Maybe this had something to do with one of these bodies being seen, perhaps could have had something to do with the establishments of some of those ancient astronomical dates, like the long count calendar. Who knows? There's been all sorts of seriously entertained theories about it over the years. And that gets us up to the formation of the moon. And so, let me see if I can get this going. This was NASA's video from 2012 of the formation of the moon. And it pretty much starts as a red-hot orb. And, oh, come on. And it's basically, the story up till then was that it formed at the initiation of the solar system. Oh, what a bummer. This isn't going to work for us. And it sort of goes through these different phases of being peppered by different asteroids, and you end up with something approximating what we see today. But today, oh, did it? Come on. Yeah, this is a cool video. I want to show it to you guys. Come on. Okay. So there we go. I believe so there's this long-held belief that the solar system kind of all formed together at the same time. And there's good reason to believe that, by the way, although it's hinging on some assumptions that may go into the graveyard in your lifetime. And so you have these different bombardment phases, which essentially build the surface as we know it. And there's different phases of bombardment, which is quite interesting, because again, that brings in the Oort cloud and the asteroid belt as to why were there moments on Earth and on the moon where it was getting peppered like crazy with asteroids, and then moments like today where we're more or less unscathed. If we were getting hit like this every 5 minutes, there wouldn't be time to have a city, let alone a life, any kind of life. Right? So the moon is very differently shaped, and so this all started with impact theories, right? And there was some ideas of volcanism that were brought in recently. You'll find those if you read about the formation of the Earth today, that one side is more volcanically active than in the past. But in general, planetary scientists have a habit of treating everything as an impact, which is not unreasonable, because obviously you look out at the sky and all of these moons do seem to have craters all over them. And yeah, it's starting to shape up, slowly becoming the moon that we see today. Now, there's some problems, though. If you treat the moon as having formed at the same time as the Earth, then you have to imagine that the moon was captured by the Earth. Now, this turns out to be a real crisis, because if the moon was captured by the Earth, there just hasn't been enough time to get this wonderfully stabilized orbital system that we see. And we'll look at the orbital system, or its orbital pattern in a minute. But it's essentially this, the moon is tidally locked. Its same side faces us. It orbits with us. And it's just inconceivable mathematically to pull off that kind of stability in such a short amount of time. So people have kind of moved past that. And the present idea, let me see if I can get this next video played. The present idea is actually that there was another planet in the solar system called Theia, which was hovering somewhere just before Mars. And over the years, this is still supposedly in the early solar system, it made its way spiraling in towards Earth and actually had a little bit of a fender bender with the Earth. Wham. And this sent all sorts of debris into a nice circular orbit around the Earth, which is it's nice because in a way it updates our problem with the composition. So I didn't mention this, but the moon, and you asked what the moon is made out of. Well, it's made out of very much the same stuff as our own mantle. And so the question is, and our core too, for that matter. So the question is, how do we share so much similarity with the moon? And so this sews up some of those problems. Depending on who you talk to, it may or may not sew up the problem of the orbital stability. Again, getting a big cloud of debris to form into a beautiful ball that's able to tidally lock with the Earth is a real a trick of coincidence. You really need to have circumstances be ever just so. And that's not to say that they're not just so. I mean, there's a good argument in everything cosmological and everything astrophysical called the anthropic argument, which is just that, hey, if it wasn't just perfect, we wouldn't be here. And I don't think that's unreasonable, but it's sort of dissatisfying at the same time. So Theia has, in the last decade, become the predominant model for how the moon was formed. Now, that's really something if you think about it, right? I mean, this is since I was in college. So people are learning completely new things now in that short amount of time. And, there's wilder theories on the horizon, too, that the moon was perhaps at the core of some larger gas giant or something like this, right? And the problem with these theories is that the time that it takes to evolve something like a gas giant into a moon, right? It's extraordinary amounts of time, perhaps longer than our solar system is dated to form. And so we're very much hung up on this dating regime because we have this phenomenal dating mechanism, a dating technique that we use on Earth called radiometric dating. And without completely boring you to death with the details of that, it's very reliable. It has internal checks, so you can basically look at how different isotopes, different atoms of different weight will decay in a predictable fashion, particularly uranium and how it decays into lead. But you can also look in the same crystal that you analyze of how lead decays into a different isotope of lead. And so you have two different lines of dating which when they intersect, you can be fairly certain that you have some relative certainty about when something was formed. And what's interesting is that all of the dates of everything we've ever found ever never reach past 4.5 billion years. And so 4.5 billion years just simply isn't enough time to neatly explain a lot of the features, right? You look at the moon, it looks very, very old when you look at the moon. You compare it to even some of the gassy planets, and really even you compare it to Mars, or and there's ways to explain away those things. But what's interesting is that they're starting to find asteroids which are coming from outside of the solar system. So there's a gentleman I know, we had him on the podcast. He's from Harvard. His name's Avi Loeb, and you might have heard his work in the news a little bit because a couple of years ago they discovered this big elongated body moving throughout the solar system, which appeared to come from interstellar space. It's called Oumuamua, which I suppose is a Hawaiian word. And it didn't seem to behave like an asteroid. And so Avi was like absolutely keen on the idea that this was some sort of alien probe that was coming through. And somehow he didn't get driven out of Harvard for this. And it did behave very strangely. Like it didn't seem to linger in the same way in its orbital pass around the sun as one would expect. So anyways, Avi has found 3 different bodies in the last 10 years that appear to have come from outside the solar system and have crashed into the Earth. Now, this makes a really interesting conundrum for the dating regime, because if we're saying that every asteroid every meteorite that we find on Earth is from the initiation of the solar system, since they all date to 4.5 billion years ago, well, if we're getting asteroids from outside of the solar system, why are those being mixed in, and why do they appear to be dating to 4.5 billion years? Right? There's something strange going on there. And so it turns out that one of the basic assumptions of radiometric dating is that you have to assume all of the uranium, right? Uranium's an enormous atom, very unstable. You have to assume that all of the fresh uranium is from the initiation of the solar system. If any fresh uranium comes into the system since the initiation of the solar system, all of your dates will be skewed inappropriately, because you're basically resetting your timer all of the time. And so there's a number of people who are convinced that this is happening. There's a number of people who are convinced it's not happening. And there's a number of discussions about how it could be happening. There's even a Stanford geologist who just retired named Peter Strzok, who insisted that he found the solar cycle, right, the changes in the sun's magnetic field, how that was actually affecting radioactive decay on Earth in his laboratory. And so, all of this is a long roundabout way of saying that we don't know exactly. We can't say with certainty almost anything, but we're increasingly skeptical about how old things are, right? And this goes back to, because at some point you run into problems because you run into the Big Bang, which is the standard cosmology right now. And this new telescope they've thrown up into space, the James Webb, has found some really interesting anomalies, which they're still trying to sort out. It's only been up there for a few months, and they're processing all the data. But it seems like there's things that are farther away than they should be, or older, because remember, distance and time are related, perhaps older than what we thought was the beginning of the universe. And if that's the case, if the universe is extremely old, let's say the universe turns out to be trillions of years old, not billions of years, well, then you have a lot of time to form a lot of these bodies. You have the possibility that some of these bodies could have been captured up, right? The solar system maybe didn't form all at once. Maybe it grabbed planets from the Oort clouds of other places. Maybe what we're looking at is actually a huge dynasty of planetary bodies that come from all over the place. Maybe some of these moons are just ancient, super ancient. And as far as like the compositional different similarities between the Earth and the Moon, well, there's the idea of convergence, where maybe there's only one way that you get something that dense, and it's through a similar process. And so they're not actually from each other, but they're actually this is the way that you get a planet that looks like the Earth, or a way that you get a planet that looks like the Moon is with those compositions. Maybe in all likelihood, it's probably a combination of all of these things. Maybe there was a collision with the planet. Maybe the planets were very ancient. It's all very much up in the air. So if anybody's really hot on this stuff, there's so much work to be done about it. And I think that's really exciting. All right, so let's talk about the Moon as it goes around the Earth, because this is what the rest of today's class is going to be about. The Moon, as you can see, doesn't have a perfectly spherical orbit. Why should it? No, nothing does, right? We talked about the elliptical orbits. The ellipse itself precesses, it moves, and you can see this a bit in this drawing. It doesn't exactly overlap itself. And this is a particular type of precession called apsidal precession. And there's another type of precession where the plane actually changes. And so, by the way, the apsides, where this comes from, apsidal precession, the apsides are the orbital points that are closest, and the farthest points are the apoasis. So when it's nearest and farthest away from us. So there's something really quite interesting here. So the orbit is sort of inclined at about let's say 5 degrees on average, like this. And so these should have overlapped. Let's draw that a little bit better. Yoink. These points here are called the lunar nodes, where it is exactly in line. This is one of them is exactly in line with the ecliptic, and one of them is out of line. And where it crosses, we have these nodal points. And so the precession tends to drift around these nodal points. And these nodal points are going to become very important when we talk about eclipses later, because you don't see eclipses every single time that the sun and the moon and the earth are in place. And that's a really interesting thing that people have actually found a way to predict for many, 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 many years without exactly understanding the orbits themselves, just because they're so regular. And this is, of course, the precession of the orbital plane. It's called the nodal precession. So this is the wandering of the plane of the moon's orbit. It's quite beautiful. Okay, so what does this look like from where we're at? And this may be something more practical that you can bring to your daily life. And I want to take just a moment to walk through this diagram from a few different perspectives. So what you see on the inner circle is the actual illumination of the moon from the sun. And you can see it's rather boring, actually. There's always one part of the moon that's being illuminated from the sun, one half of it. But on Earth, we see something very different. And you can play with this. I thought about trying to demonstrate this, but I didn't know if you'd be able to see. But if you just take like a tennis ball or something and shine a flashlight on it, and you move it around, you'll be able to see actually the different shadows. You'll see each one of these phases appear. And I think that we should maybe just talk about each one of these phases a little bit. So the moon's about 30 days it takes to go around the Earth, and so that means it moves about 12 degrees, which is about 24 times its own diameter each day, each night. And so it's going to rise in a slightly different location. Remember, 24 degrees is about like the width of your spreaded hand. And so the way that we measure the moon is in these phases of the moon, and there's quarter phases. And interestingly, several indigenous American cultures actually didn't even have days of the week in the same sense that we have 7 days of the week. They just had days of the week based on the phases of the moon, which makes a ton of sense because you can always see what date it is every night. And so the moon is a little bit behind the sun. It rises by quarter moon. It's rising a little bit later, around noon, and sets around midnight. And then we see more and more as the phases progress. This is called waxing as it's growing. And then by the time that we've reached halfway to the full moon, we're calling this a waxing gibbous. And this is, I believe, a Greek term. Is it Greek or Latin? It's Latin. Okay. It means hump. So it looks like it has like a little bump on it. And then by the time that the moon is on the far side of the Earth from the sun, it's being fully illuminated. All of the sunlight is reaching it. Now, of course, you say the Earth is in the way, but remember that most of the time, the moon is tilted, its plane is tilted slightly away. And so it can be completely behind us and completely illuminated at the same time. So the only difference between a lunar eclipse, when the Earth gets in the way, and you have a full moon, is just the plane of the orbit. And so the only time that you ever get eclipses is when the ecliptic plane lines up perfectly with the plane of the moon's orbit. What else can we say about this? Let's look at it from a slightly different perspective. So this will give you a little bit of an idea of exactly where the moon is with respect to the sunlight at each one, if you can't visualize it from before. And you can see it coming from over here. Now this is, of course, the opposite of what it looks like from Earth because you're looking outward at it. But at each phase, you can see that the moon is still halfway illuminated each time, but we're seeing a slightly different perspective on it. And what's really fascinating is that it doesn't really matter where you are on Earth, you see the same phases of the moon. So this is a fantastic timekeeping mechanism because you don't have to reset your clocks for time zones and so forth. It makes a lot of sense. The problem is it doesn't line up with the solar year, and that's why we had the calendar cataclysms that we talked about. One more perspective way of looking at this has to do with the moon rises, which are approximately 50 minutes later each night, and the moon moves eastward. And so you can track this and start paying attention to it in the sky and really keep an eye on which phase it is, and you'll be able to really start to lock up how well and how poorly the months line up with it, because it's very close, but not quite right. There's also this concept of the harvest moon, which you've probably heard about, which has to do with the angle at which this plane is inclined over the year as the seasons progress, such that in the fall, there's this lengthening of the moon, and so the rise is actually drawn out much more due to the obliquity of this angle as seen from the Earth. This is quite useful for farmers because I guess earlier on, before electricity, they were able to perform their harvest longer and start earlier. So, I wanted to maybe just read just a minute about how other people have made sense of this too, particularly the people who lived here before Western civilization had a kind of different take on the moon. And if you'll bear with me, I want to just bring in that perspective for a second. So, what's really interesting is that the moon, when you stop thinking about it as a material object and you start thinking about it as a symbol, you can actually bring in a whole new level of information which can be transmitted to the people. I mean, how many folks today just ignore the moon? It's pretty and stuff, but it's not particularly meaningful to most people. And we really have like quite a crisis of meaning in the West right now. People, so many people. I mean, there's millions of YouTube videos about how to find the meaning in life and all of this, right? It's a huge crisis. What does it mean? What am I supposed to do with my life? That didn't seem to be a problem for indigenous cultures because your meaning of your life was quite obvious. You made sure that the universe continued as it was supposed to, and of course that meant subsistence, but it also meant looking after the sky and actually taking care of it, and we're going to talk about how eclipses in almost every indigenous culture were seen as an active participation event where people had to actually make sure that the sun came back. So everybody would get out there and work to get the sing and try to get the sun to come back because it was such a participatory experience. So this is from the Navajo tradition. The first man and first woman brought the energy of the sun, moon, and a crystal star from the first world. In the second world, Coyote, first boy and first girl, were created, and together they brought the knowledge of heat and light from the clear crystal to the fourth world, that's our world, all of which was eventually used to produce the sun. The holy ones decided the sun would have male characteristics and would provide order to the days and seasons. And so the seasons were, of course, recognized by the location of the sunrise. The moon was referred to as the first traveler and was created to provide another source of light at night and to provide another measuring tool. The Navajo recognized that the moon has shorter cycles compared to the sun. Because of the 28 to 30-day range of the moon's phases, the moon provides 13 months. Nature and human activities on Earth were used to name the months. Because of its gentle character and direct correlation with women's menstrual cycles, the moon is considered female. The moon provides guidance and knowledge that complement the sun. Day, night, months, and seasons are signaled by the phases of the moon. The holy people agreed that the moon would be both grandmother and grandfather, dominate old age, and act as a precursor to the unborn child. each day of the month is named with regard to the phases of the moon, like I said. During lunar eclipses in the Mayan and Aztec world, the pregnant woman would actually have to put obsidian in their mouth to protect their unborn children because it was so tightly tied in to the fertility cycle. So it's really interesting that you see the feminine attached to the moon in almost every single culture, and the masculine attached to the sun. And I'm sure that that is deeply meaningful in times past. And I invite you to consider all of the reasons why this came about. I mean, obviously, the pegging of it to the menstrual cycle is uncanny at best. I don't know if we'll ever get to the bottom of that since we live in these artificial lighting environments. I don't know if we'll ever be able to make sense of it. So the moon is a rock to our culture. The moon was a very significant entity in most former cultures, particularly in the ones that lived here before the West arrived. But back to the moon as a rock. So we talked about gravitation a bit, and it turns out that gravitation is really important in terms of what the moon does to us on Earth. And one of the biggest points is the tides. So gravity seems to function as a product of distance. We talked a little bit about why that might be, especially if we think about atoms as being connected to one another. And your connectivity is going to scale with how close you are to something. In this case, the near side of the Earth is going to pull a bit more than the far side, and the pull is mutual. And so this actually causes the Earth to be slightly elongated. It's shaped a little bit like a football, an American football. However, the stretch is very minimal. I think your textbook mentions that if the whole Earth was made out of water, you could get a pretty serious stretch. But in our case, it only amounts to about 20 centimeters, right? Because the whole Earth isn't made out of water. It's made out of a very difficult to deform rock with a density that's something like 4 times more than the sun. It's hard to actually find a lot of things that are as dense as the Earth, which is something to really ponder why that would be the case. So tides are a really interesting thing because what you see is not necessarily that the side that is near the moon is that which is getting stretched. The opposite side is getting stretched as well. And when I first learned about this, it took me a minute to make sense of it. But what you have is that the Earth is spinning. And so this brings back our concept of inertia that we talked about in one of the earlier lectures, where things that are in motion, they want to stay in motion. This is very much related to their gravitational interaction with all of the bodies in existence, or at least all the ones around them. So things are being held in place, right? My arm wants to stay where it was when I turn my body. Everything is being held in place. And so just so, the leading side of the Earth is swooshing ahead, and the side that's trailing is being pulled by the moon. Now, this explanation, which is given in almost every textbook, is it's sort of fatally incomplete because while these processes do play out, the Earth is not this wonderfully evenly coated body of water, right? There's continents, and there's recesses, there's different depths of the ocean. And so what we actually see is something that looks more like this, where the higher the tides are in the darker colors in the red, and the lower ones are in the blue. And it's actually quite chaotic. Here's an animation of it. Of course, winds and storms play a huge role as well. There's places that don't have tides at all, which is very strange. And so this is actually what you see over the course of, let's see, looks over 24 hours, I suppose. So it's not perfect, but I think that the processes are sound. I think that the pull and lag and the interplay, again, between inertia and gravity, the significance of the relationship between inertia and gravity can't be understated. It's a really fascinating portal into how things work in the universe, and we're going to do a lot of that in the cosmology course next semester, especially when we start to try to understand general relativity and where that came from. But you have this, again, this fine-tuned balance. Just like the orbit of a planet has very much to do with its forward inertia versus its inward pull of gravity. It's this delicate balance. You also have the same sort of thing happening with tides, such that, the bodies of water are somewhat stable, right? Because if they were being completely pulled off to one side, it would just be a disaster. You'd have tsunamis chasing the moon around, and it would just be nuts. Okay, so there's also this phenomenon which is worth mentioning. There's actually a lag. This also has to do with the inertial capacity. The Earth is rotating faster than the moon, and so that cohesion of the water carries the bulge a little bit ahead of the moon, actually, which is, again, impossible to imagine without this concept of inertia and understanding that the Earth is going way, way faster. Remember, the Earth rotates every day. The moon rotates around the same point only every 30 days. There's also this idea that there's different tides. So if any of you have been around the ocean much, you're probably aware of this idea of neap tides and spring tides, which are really something to see. I used to spend a lot of time down in the Bay Area, and I have a friend who lives over in Bolinas, and driving out there through Marin, every once in a while, you get these king tides, which just absolutely inundate the highways and everything. It's really quite wild to see. It feels quite cataclysmic. This has to do with this amazing conjunction of the sun and the moon being aligned perfectly, such that you get the pull of both of them on the body of water at the same time. Of course, the weakened tide, this neap tide, is when the moon is at a 90-degree angle. And this somewhat lessens the effect. So, I saw this story in the news this week. I thought it would be worth mentioning too, which is kind of cool. The water that's on the surface of the Earth isn't the only water that we have on Earth. In fact, it's becoming increasingly apparent that there's something like maybe as much as 6 times as much water as the oceans inside of the Earth, in these transition zones between the different layers of the mantle, which is something worth considering. So, these are said to be existing in the form of a hydrated form of magnesium called ringwoodite. So they're not liquid water in the same sense that we'd think about it, but they do have enough liquidity to provide viscosity to explain some of the different convection cycles that geologists suspect are important in the tectonics of the plate. So I don't know. It's interesting to think about how this might also be playing into the tidal system, into things like tectonics and earthquakes and so forth. I think we're going to discover very interesting things in the next century about this. What do I want to say about that? Not too much, but it's really something to think about. This is brand new understanding too. Just the idea that there could be so much water deep within us. I forgot to mention too, one of the tenets of that Theia hypothesis with the formation of the moon is that that's where we got our water too. So for most of my life, when I was reading textbooks, the water was said to have come from comets, right? But that was difficult for me to swallow even as a kid. That's a lot of comets if you've ever been to the ocean before. It really stretches the mind to imagine how that could happen. So coming up with as we update our planetary formation models and we come to understand these things better, maybe we'll understand where this water is coming from also, because a lot of this water isn't on the surface of the Earth, and it's not totally clear how it got there, which is cool. All right. So another thing that's interesting is that the Earth is also pulling on the moon also, right? And that's having effects on the moon. And so the consequence of this is that the friction of this interaction is actually slowing the rotation of the Earth. Now, this is a problem because we talked about how angular momentum has to be conserved. You can't just slow something down without either the lever arm changing, which is what you see in this figure skater, right? She speeds up when all of her center of mass is close, and then as the lever arm extends, she can slow down, or vice versa. And so the thought is that to balance this, the moon is actually moving away from the Earth at about 4 centimeters a year. And at some point, it will be gone, is the thought. And the question is, first of all, that's not going to happen for billions of years. But what will happen? In something, at some point, the day will slow down, and the month and the day will be the same length, which will be quite interesting before all this happens. Do we need the moon? Do we need the tides? Well, it seems like the moon actually does a good job of stabilizing our orbit. It keeps our plane inclined in a very useful, stable fashion, such that our seasons aren't varying wildly like they could be. And so, yeah, maybe we'll have to find a new home by the time that happens. Right. Yes, but the problem is our record keeping is so shallow, right? And at only a few centimeters a year, the changes would not be perceptible on our record keeping scales. I mean, we've had modern range, so how do they measure that? That's an interesting question. They actually, some of the astronauts, when they first went to the moon, put a little mirror on the moon, and they actually use a laser that they shine off that mirror, and by the changes in the phase of that laser, they can gauge the distance to the moon. And so that kind of precision that's necessary is so new. And obviously, gravity is a very weak force at these distances already, right? The Earth, moon's, the moon is much further away than it's looked in all of these pictures we've shown. And this is sort of difficult to grasp because it's unbelievably far away, despite how close it looks. It's something like 60 Earth radii away from us. It's very, very far away. So when you're talking about something that's 60 Earth radii away from us, which I think is Earth radii is like 6,000 kilometers, I mean, this is an unbelievable distance, whereas a few centimeters, what difference will it make, except over billions of years? And by that point, hopefully we'll have figured something out. I mean, just imagining humans existing for billions and more years is quite a feat to pull off. We very much want to kill each other off right now still, which is, it's a real problem actually. It's hard to imagine. There's certain conflicts on Earth which have existed so very long. It's going to be wild to get past. If we get past them, I think that we'll have a good shot. But eventually we'll. And people are already looking for new Earths. This is a whole topic we'll talk about when we get into the more planetary side of things. There's a lot of them. There's a lot of very Earth-like looking planets out there, and we can't really see them great with our telescopes, but we can see the effects they have on the nearby stars and on other planets that are passing by. And we can make some rudimentary guesses about their atmosphere and so forth. But we're going to have to find a new Earth at some point. There's no way around it. This one just won't last forever. But we should take care of it in the meantime. I mean, I'm talking billions of years away, too. This is, a billion years is 1,000 million years. A million years is 1,000,000 years. This is just, if our recorded civilization dates back to the Greeks, maybe 3,000 years ago, I mean, think how far we've come. It's very difficult to imagine what things will be like in that amount of time. Well, maybe we won't even, who knows? Yeah, I shudder to even guess what. Maybe we'll just be little brain blobs in giant robot suits, or who knows? I mean, one thing that's worth considering is that if we're even going to go and explore some of these star systems, we're going to have to do it intergenerationally, because there seems to be a fundamental limit on how fast we can move, no matter what you are. Even if you're just a tiny little particle, you can't move faster than the speed of light, and there's reasons for that. We can play with why that is, but it seems to be fundamentally impossible to go beyond a certain speed, which means that, if you're going to make it to some of these habitable planets, well, you're going to have to send yourself, and you're going to have to have your children or their children's children be the ones who actually explore that planet. So you're going to have to pack a lunch, right? It's going to be a long trip. Okay, so I of course am running out of time a bit, but and I think that we've more or less talked about why you get lunar eclipses, and so I'm not going to dwell too long on those. Again, when the moon is between the new moons happen when the moon is in the middle of the sun, I mean between the sun and the earth. This is when it's dark, right? And lunar eclipses happen on the other side when the earth is in the middle of the sun and the moon, but they only happen when the plane is inclined at this perfect zone. And this means that lunar and solar eclipses, and solar is of course happening back on the new moon side, they're happening with similar frequency. The problem is we don't see a lot of them because they happen where you're not at. And this is a nice little schematic of how this happens. At some point, the Earth casts this nice shadow across the moon. Have any of you seen a lunar eclipse? They're pretty cool, right? Not half as cool as the solar. Anybody seen a solar eclipse? Oh, cool. Wow. Wow. That's amazing. I haven't. Jeez. Yeah. The last one I was in grad school in New York City. It was kind of a drag. I couldn't go see it. I had some friends who drove all the way out to the Midwest to check it out. You guys had a pretty good view out here in Oregon, though, huh? That must have been amazing, huh? All right, so we'll talk about solar eclipses. Again, I drew this on the board already. These are the lunar nodes that have to coincide. There's so much folklore associated with eclipses. Famously, Christopher Columbus, when he was coming over and trying to worm his way into the continent, he made use of an almanac which had been tracking these to perform a little bit of a magic trick on the people of Jamaica. They were actually putting him up because his ship was broken down. And he'd been there for about 6 months, and they started to not like this guy, and they started to cut off his food supply. And he basically told him that, or he told the indigenous people that were hosting him that, if they didn't start taking care of him, that his God was going to come and smite them. And they were like, yeah, whatever, your God can't do anything. And he was like, oh yeah? It's going to be the moon's going to be blotted out tomorrow night. And it was. And this really stirred them to their core. And for better or for worse, the rest is history. I'm not even going to dive into the conquest of America. This will definitely kill the rest of the class. So when it comes to the solar eclipse, there's something really fantastic, which is this really amazing coincidence, if you think about it, which is that the angular size of the sun and the moon from our perspective are about the same. Right? So if they weren't, if the moon was for some reason smaller, a little bit different distance, and of course this is all going to change as the moon moves away for billions of years, you wouldn't have this same totalizing effect where it covered it perfectly like this. And I've thought a lot about this, about just how amazing this coincidence is. And perhaps there's some geometric explanation for why that's such a stable point. And maybe it's more stable than we think, actually. But as you can see from your perspective over here, despite their size differences, this angular half degree seems to hold up. And this makes for some amazing stuff. Let's see, will this one play for us? This is just a nice little animation of really how rare this event is. So that shadow, it's always being cast. And it's a tiny little shadow. And you can see that in this case, it's barely going to trace a little pinhole across North America. And this is what we experience as the solar eclipse. Now, sometimes the distance of the moon is closer. We talked about how it's an elliptical orbit. Sometimes it's closer during an eclipse than other times. And when it's very close, we get a total eclipse. The entire sun is blotted out for a few moments. And otherwise, you get something which is called an annular eclipse, annular eclipse, where you can see sort of a ring around it. I'm sure both are absolutely astonishing. Okay, so there's 2 to 5 of these that happen every year. We just Some of them are partial, some of them aren't noteworthy, some of them happen over the ocean. And so on average, there's one about every 18 months. And I hope that all of us who haven't seen one will eventually get to see one. There's a moment, of course, during the eclipse, and there's a location where you don't get total darkness. And this has to do with the interesting light dynamics as the light is refracted through the atmosphere, right? And there's a small semi-shadow which is being cast. The darkest shadow is called the umbra, which is what you need for that total eclipse, that real darkness that happens. And then there's the penumbra, which is this more diffuse shadow. It's kind of cool looking from space, too. It looks like an evil black hole or something. So, I want to just close with the fact that these eclipses were extremely significant for all of history and almost every culture. And again, people saw themselves as necessary participants in making all of these things happen. I want to read you, to close out, a little piece from the Florentine Codex, which is one of the few surviving manuscripts from the Aztec culture, about what it was like for them when the solar eclipse occurred. And you can just imagine, this is without any material understanding or conception of what these bodies are. They seriously represent something bigger than people to these people. And so from the Florentine Codex, the Aztecs wrote, "When the eclipse came to pass, the sun, which was the god called Tonatiuh, turned red. He became restless and troubled. He faltered and became very yellow. There were tumult and disorder. All were disquieted, unnerved, frightened. There was weeping. The common folk raised a cry, lifting their voices, making a great din, calling out, shrieking. There was shouting everywhere. People of light complexion were slain as sacrifices. Captives were killed. All offered blood. All offered their blood. They drew straws through the lobes of their ears, which had been pierced. And in all the temples there was singing of fitting chants, uproar, and there were war cries. It was thus said, if the eclipse of the sun is complete, it will be dark forever. The demons of darkness will come down, and they will eat men. And so the people had to make it pass. And they all worked very fervently together to make it pass. And so I think that this is a very great unifying feature for these cultures, which actually even today, people come out from whatever they're doing and experience these things together. And I think that's something we could use more of in this world, is something which takes us all out of our individual little politics and hobbies and friend groups and puts us as humans against something. All right, let's stop there for today, guys. Thank you very much.